Yes.
Thank you. Okay, let's get started. It's my pleasure to introduce Alvaro Velasquez, who leads the machine learning intelligence portfolio of investment at AFRL in the US. In his capacity, he manages and proposes new research directions and technology transitions for the Air Force in the field of AI and autonomous systems. This entailed close collaboration with both academia and private sectors. Alvaro received his PhD in computer science from the University of Central Florida, and he holds an interdisciplinary research record, including publication in AI, optimization, networking, cloud computing, and logic and circuit design. Alvaro is a recipient of numerous research awards, including NSF GFRP Award, the University of Central Florida 30 Under 30 Award, and the Best Paper and Patents for, and several patents from AFRL. He serves as Associate Editor for IEEE Transaction on AI, and his research is currently funded by Air Force Office of Scientific Research. Please welcome Alvaro. Thank you.
Alvaro, do you mind turning on the camera?
Yes. That could be tricky. Yes.
Good.
There we go. I can see myself. And
You could use these two.
to switch the slides, yeah. Okay, very good. So thank you, Ashutosh, for the introduction, and thank you everyone for coming. I'm going to be presenting some of the research that I've done for the past couple of years that looks at how we can sort of integrate these powerful deep learning systems that have been sort of taking computer vision and NLP and reinforcement learning and all of these machine learning subfields by storm since about 2011, 2012, and how we might be able to integrate some formal linguistic structures to help guide the learning process, make the learning more efficient, and provide some other benefits as well. Before I get into the details of this, I want to give a quick introduction to add to what Ashutosh mentioned. I lead the machine intelligence portfolio of investments for the Air Force Research Laboratory. So in this capacity, I oversee 4 programs. They're all fairly large investments. Each program has a broad agency announcement associated with it. It has its own prototypes and all kinds of things going on under it. But I very quickly want to mention what some of these programs entail. We have interactive learning for mission planning, which basically looks at how you might best leverage the human expert or the domain expert in order to help label your data in data scarce environments. This is a very common setting in the Department of Defense. We oftentimes don't have access to the best quality data. Perhaps it hasn't been properly curated, or perhaps is a classified data set, and so on and so on. So oftentimes we have to deal with this problem of data scarcity. Here we look at techniques, for example, from active learning, from imitation learning, where we ask the question of how we can most intelligently query the human operator to help us label data. One simple example is if you have a learning model and you feed it a piece of unlabeled data, and the output of the learning model resembles the uniform distribution, then we know that the model doesn't really know what the heck is going on, and we should probably send this to a human expert to label the data. So we've had a lot of success in that effort. We have the Stratagem program that looks at how you can do traditional AI-based planning for multi-agent engagements in board game-like scenarios. These are known as war games in the Department of Defense. They're basically the board game equivalent of some kind of military relevant engagement. These can have air units, land units, sea units, and it functions very much like a board game would. We have Streamline ML, where we are developing a machine learning ecosystem so that end users across the DoD can upload and download data, models, training algorithms, and thereby facilitate the adoption of machine learning. And finally, we have operationalizing machine learning for C2, or OpML, where we're looking at sort of these quick and dirty prototypes that we might develop to help the warfighter, to help the the human operator in various engagements. So all of these are very big programs. And during the time that I have overseen these efforts and proposed some of these as sort of applied research investments, I've also recognized that there are some significant limitations that we need to address, certainly within the Department of Defense, but even more broadly for the mass adoption of autonomous decision-making solutions. So the DoD has mostly spent its investments in what I would call the data analytics side of things. This is more conventional machine learning problems like you see in computer vision and natural language processing, things like classification problems, regression problems, text summarization, and so on. But increasingly, I'm trying to push this machine intelligence portfolio in the direction of autonomy, which is where you have an agent interacting in some environment. The agent must make actions in the environment, observe the consequences, and reason about some long-term objective. So this is a very different domain than the more conventional data analytics domains. In particular, there are at least two very big challenges here, in that, of course, as the agent makes a decision in its environment, it's essentially changing the future data distribution that it observes. If, for example, a blue aircraft takes down a red aircraft, you're not going to see the red aircraft again for the duration of the simulation. So you're changing future data distribution as you take these actions, but you're also reasoning about some kind of long-term objective that is a result of many actions, right? So in the case of chess, for example, it takes many moves before you can finally land a checkmate. So how do you assign credit to the intermediate states and actions is not immediately obvious, not like it is, for example, in classification problems where everything is solved in one shot, right? You feed an input through your learning model, you observe some inference result, you can compute an error, and you can backpropagate that error to train your learning model. In reinforcement learning, it's sort of a much more complex problem. Now, autonomy is generally the domain of fields such as reinforcement learning, which can be broadly construed as autonomy without a model. So this is the setting where the agent must interact with the environment, and the environment is essentially a black box. You observe a state, you take an action, the environment gives you some kind of reward, and it gives you the next state. The reward signal here acts as a sort of proxy for the underlying objective that you're trying to solve. In the case of chess, for example, you can have very simple rewards like a +1 if you're in a state and you take an action that allows you to checkmate an opponent, or -1 if you get checkmated yourself, and perhaps a reward of 0 everywhere else, right? This would be a very inefficient reward, but it's technically a correct reward signal. Then you have the area of planning, which is autonomy with a given model. So here you know exactly how the dynamics of your model works. This is, for example, the domain of board games, chess, Go, where we as humans, we know exactly what the dynamics are, so we can plan ahead multiple moves in advance, because we know exactly how our adversary might behave. At any rate, we know exactly what the legal moves for the adversary are, and so we can plan ahead. So even though these two fields are somewhat related, and increasingly there's a large intersection between the two, generally the methods can be quite different, and there can be different advantages to both fields. So why do we want to go in this direction of autonomy versus data analytics? The reason is because we've seen these tremendous successes since about 2013 in the fields of reinforcement learning and planning. So starting with 2013, this is when DeepMind developed their DeepQ networks that allows an agent to go from raw pixel data, which in this case is highly complex. It's 84 by 84 pixels. Each pixel can take on a value between 0 and 255. And you're observing the last 4 states of the agent. So the state space is 256 to the 84 times 4 times 84. It's a completely massive state space. And yet DeepMind was able to solve this problem and actually achieve superhuman performance in various Atari benchmarks. This was before they were bought up by Google. And I suspect this particular paper, which was published in Nature and is very famous now, was the reason why they were eventually bought up by Google, I think the year after. Then you have a very impressive planning solution, which defeated the world Go champion. This leverages Monte Carlo tree search and some neural network-based learning, which I'll go into more detail as to how this particular method works. And it was able to defeat the world Go champion. You have the Liberatus, which was able to defeat top poker players. This is the work of Thomas Sandholm from CMU. And in particular, it's challenging to solve poker because it's a partially observable game, right? You don't really know the cards that your adversaries have. There's multiple agents, and so it's somewhat complex, even though the representational complexity is not too high because you're just reasoning about the values of various cards. And perhaps the most impressive of all, certainly from a complexity standpoint, is the work of OpenAI 5, which defeated Dota 2 champions, and DeepMind's AlphaStar, which defeated top StarCraft 2 players. These are real-time strategy games, 2 teams. Each team has multiple units. Each unit has its own properties, characteristics. There's micromanagement, there's macromanagement. It's a very, very complex game. And DeepMind and OpenAI were able to crack it. But there's a reason why, when we look at this table, 4 of the 5 methods that we see here come from DeepMind or OpenAI. It's because it is incredibly expensive to achieve this level of success in reinforcement learning and planning. It's feasible, but it's just very inefficient and very expensive. The only exception here is Liberatus, the work from CMU, because as I mentioned earlier, the representational complexity is actually not that high. The tensor that represents your input space simply represents the values of your cards, the values that are observed from the opponents, and for the cards that are unobserved, you have some kind of dummy value. So the representational complexity is quite low. And to go into more details, here we have the case of AlphaGo. So over 10 million games were required to match the performance of a human. Now, of course, we don't know what a human would look like if they could play 10 million games of Go. Presumably, they would be able to beat AlphaGo. What does 10 million games of Go mean? There are some estimates that the power budget just to train this system, something like $5 to $10 million. So immediately this puts it out of reach for the vast majority of academics. Even within the Department of Defense, you can't really ask for a large budget by saying that you need $5 million or $10 million just to train your agents. It's a complete non-starter. And that's just the tip of the iceberg. So here we have the OpenAI 5 bot, which collected 900 years of data per day for a total of 45,000 years worth of data, which is a ridiculous amount of data. And of course, this requires a lot of time and a massive energy budget to be able to train the systems that would actually leverage 45,000 years worth of data. I haven't been able to find any estimates as to what the power budget was, but it's certainly in the tens of millions of dollars. And worst of all is AlphaStar. When you read their paper, they say that 250 years worth of data was required per agent. But when you do the math, they actually have to train many agents. They put the agents together into what they call league play to compute their ultimate mixed agent. And once you do the math, this turns out to be over 60,000 years worth of data. Worse yet, they actually need a human prior. So for AlphaStar, you don't just need this massive amount of data, but you need approximately 1 million replays from the top 20% of humans. Without these replays, even when you have this ridiculous amount of data, the system actually performs very, very poorly. So with no human data, here you have your ELO score of 149. Any of us in this room could beat AlphaStar if it doesn't leverage human data first. So really what AlphaStar is doing, more so than just deep reinforcement learning, it's a sort of imitation learning or a deep refinement operation that first leverages the human prior as to how you micromanage, where you send your units, what you build and collect, etc., and optimizes around that human prior. So this is to paint a picture that while we have come very far in autonomous decision-making, in reinforcement learning planning, there's still quite a ways to go. And right now, this complexity really puts it out of the reach of most people. Most academics can't afford to implement such powerful systems. Most people within the Department of Defense, most people in the private sector can't do it. You have to have tremendous, tremendous budgets for this. So there's clearly a need for more efficient decision-making. And we can turn to the early successes in neurosymbolic AI, where we are seeing increases in efficiency, among other things, in the data analytics side of things, in your computer vision classification problems, in your NLP problems, text generation, visual query answering, this type of thing. So for example, here I've listed three random examples of the early successes of neurosymbolic AI. First, we have the work of visual query answering, where you take a scene and you do some kind of unsupervised object detection, determine where the objects are, determine their relative positioning, and use long short-term networks to encode the semantic relationship across the objects. And by doing this, and the method's actually fairly straightforward. I've listed the reference there. By doing this, you can achieve a 2 order of magnitude less data than a competing state-of-the-art classification approach. You also have interpretable classification. This is IBM's logical neural networks, where you take the activation functions in deep neural networks, which encode the nonlinearities required to compute a general nonlinear function approximation to arbitrary degree. For those who be familiar, this is sort of the universal approximation theorem. These necessary nonlinearities, they simply overlay a Boolean logical operation on top of them and add that to the loss function. So that now when you train these logical neural networks, you're not just computing these parameters insofar as they lead to a correct classification, you're computing them insofar as they lead to an interpretable result. So that now instead of just saying, I think I've observed a cat, you can say I've observed the cat because there were whiskers and there was a tail and there was not a dog, or whatever the case might be, whatever the underlying logical structure of the data space that was used to train the network is captured by this logical neural network. Finally, NLP, you have logically consistent learning. Here, 2 GPT-3 agents were trained. One of them to generate text, which of course, as we all know, GPT-3 is very good at. And then another one was trained simply to maintain logical consistency across the text, so that you don't just generate grammatically correct text, but you generate text that is cohesive with the underlying narrative that was previously established. So there's some straightforward semantics that is overlaid on top of these methods. And it's worth noting that neurosymbolic AI is not really a new idea. There's been a sort of renaissance since about 2019 or so, where at AAAI there was some keynote with Turing Award winners, Jeffrey Hinton and Joshua Bengio and Jan LeCun, where they discussed the need to integrate the symbolic and the neural. But really the idea goes back to the late 80s. As soon as neural networks were proposed, the obvious thing that came next is how do we take symbolic AI, which of course was sort of that first wave of AI that was popular back then, how do we integrate the two things? It's just that now with the successes of deep learning and perhaps some of the plateaus we're hitting therein, now is the time that it's become increasingly urgent to integrate the two waves of AI. So what's the goal here? As far as my research direction for the foreseeable future, and certainly for the next 5 to 10 years, is to develop neurosymbolic autonomy solutions. So autonomy here, again, as opposed to data analytics. So we've seen the early successes in neurosymbolic AI for data analytics. We have not seen this for autonomy. So that's what I've been focusing on. So how do we develop these neurosymbolic autonomy solutions that improve data efficiency so that we can facilitate the adoption by the rest of us? Not all of us have these tremendous power budgets and resources and access to TPUs, etc. So we need more efficient decision-making solutions. But in particular, I want to ground the symbolic component in formal language theory. So what does this mean? So this means that the symbolic component can follow, for example, one of these languages. This is the famous Chomsky hierarchy of languages. This is not an exhaustive list. There are many more language types, but the weakest language you have is a set of regular languages. This is basically your regular expressions. And your regular expressions have an equivalent symbolic structured representation. as a deterministic finite automaton, or a DFA, which a DFA is basically a finite state transition system. You have an initial state, you have some accepting states, some logical conditions by which you transition between states. And if you go from the initial to the final state, then you are in the language. So these types of languages are very useful, for example, for encoding objectives in autonomous decision-making. So you have the regular languages, the weakest ones. These are represented by DFAs, and you have context-free languages, which are represented by push-down automata, context-sensitive languages, which are represented by linear-bounded automata, and the recursively enumerable languages represented by Turing machines, which of course are the most powerful. And for the purposes of this talk, we're going to focus on the regular languages. So we're going to take this automaton representation of a regular language, and we're going to feed this through our autonomous decision-making algorithm. And we want to get some policy that, you know, can be computed more efficiently than if we did not leverage the automaton. So this is an example of neuro-linguistic autonomy. And at a very high level, we might imagine that you're given some kind of natural language objective. This can be some kind of special instructions. This can be the expert of subject matter experts, whatever the case might be. And there are translation mechanisms and syntactic sugars that will translate that to its corresponding automaton. And we are making the assumption here that the automaton represents a regular language. So this is not all powerful. We can't yet just translate this into a Turing machine and solve everything, right? So let's assume we're giving this objective. We translate it to its automaton representation. We get a model of our agent environment dynamics. In the case of reinforcement learning, this would be a black box that we interact with. In the case of planning, it's the full dynamics model. We know the transition function, for example, we know the reward function, so we can plan ahead. We feed these two things to our autonomous decision-making algorithm, and what we expect to get is a policy that either satisfies the objective, which is to say, is a member of the language encoded by this automaton, or maximizes the probability of satisfying the objective. So there's a specific algorithm. This is based on the AAAI 2021 paper that extends the Monte Carlo tree search approach used by DeepMind and adds this kind of linguistic component on top of it to improve the data efficiency of the decision-making procedure. So first, I'm going to briefly cover how the DeepMind Monte Carlo tree search approach works, and then I'll explain how we extend that and get this improvement in data efficiency. So in the case of Go, you observe a board configuration in the real world, and this will be the root state of your Monte Carlo tree. So because this is the planning setting, we know exactly how the game of Go works. We can kind of plan ahead, right? As we humans do, we build this decision tree of possibilities. Each node in the tree is a different board configuration. Each edge represents an action that takes you from the parent board configuration to the child board configuration. And let's say we want to make a decision within this tree. So this tree is for all intents and purposes, it's imaginary space. We've observed a real life state, and we're building out this imaginary tree before we make a decision in the real world. So how do we make the decisions within the tree? We use this thing, this is called the upper confidence tree. It's a very basic formula. It has a Q function, which is an action value function. It tells you in a given state, i.e. a node in the tree, if I take a given action, what is my expected probability of winning the game? And it has a function U, this is known as the upper confidence bound, which is basically an exploration function because of course we always have to explore to find the true optimal and not get stuck at a local optimal. It's a simple formula. In the context of traditional Monte Carlo tree search, one can prove that if you follow this formula, eventually you will converge to the correct action. So let's say we follow this formula. We're here in this bold node in the tree. We take an action and we observe a new leaf state. So this is a board configuration we have not seen before. So naturally, what we have to do is we have to arbitrate its value, just to say, how can we compute the probability of winning from this newly observed state? Well, for the past 20 plus years, the way Monte Carlo tree search works is that you use a default policy, also known as a rollout policy, where you sample a bunch of random trajectories. And you might do something simple like computing a ratio of how many trajectories won the game divided by the total number of trajectories. And you obtain this very simple empirical expectation. And then you propagate that estimated value up the tree to the root of the tree, which is the real world stage where we want to make a decision. Right. Once we've had enough exploring in this tree, which is usually a preset value that the user will give you. In the case of AlphaGo, it's something like 1,800 nodes in the tree. Then we take an action in the real world. And we observe a new state. So this is old school Monte Carlo tree search in a nutshell. One of the observations that DeepMind made, that it's, I think the key observation is that we're generating very high quality data here, but we're not really putting it to good use. Why is this high quality data? Because to generate one sample in the real world, we have to generate all these expansions of this tree. So this isn't just any piece of data we're generating. This is a very good piece of data. So why don't we create a training data set and use it to, of course, train a neural network and replace this very ineffective default or rollout policy. So that now when we observe a new state in the tree, we can simply feed it through our neural network, and the neural network will tell us the predicted value. This is, in my opinion, the biggest insight from DeepMind's AlphaGo, and this is what allowed it to defeat the world Go champion. Now, a caveat, there are a million other hacks and little things. If you read the AlphaGo paper, there's a very large appendix where they tell you specific hyperparameters, specific little hacks and heuristics, and when they decided to just choose completely random actions and all kinds of things that seem kind of arbitrary. But unfortunately, that is part of the art of machine learning, is not everything has been boiled down to a science. But this is the key insight. Generate this training data set of high quality data from real world experience, replace the default policy, right? So what we're gonna do is, we're gonna take that system and we're gonna extend it by adding this automaton objective that will represent basically your reward signal. So what does that look like? Here I have a very simple example. Using linear temporal logic, we can generate this very simple automaton where the objective is G hostile implies F safe. So G means always, F means at some point in the future. So this means always when we observe a state labeled hostile, then at some point in the future, we must observe a state labeled safe, and you get this cute sort of trivial automaton. Here's another example more related to the experiments that we carry out. This is a simple Minecraft-like grid world where you have agents with, states with wood, states with factories, states with, where you have to build a home, and states with tools. So you want to, every time you observe a state labeled wood, at some point you must go to the factory where that wood gets converted into a tool. And you must at some point have at least 3 tools and go build a house. So it's a cute little example, but it's actually fairly complex and hard to do if you reason directly over the state space. And here you have a corresponding automaton representation with its corresponding logical conditions by which we transition from one node to another. So let's look at what this looks like in action. I call this automaton guided tree search. Let's assume we have a very simple 2x2 decision process. The agent starts here at the top right, state labeled wood at the top left, state labeled home at the bottom left, state labeled factory at the bottom right. And the automaton objective is some arbitrary objective defined over this basic alphabet of wood, house, factory, and so on. So the agent begins by making a decision based on this upper confidence tree I mentioned earlier, but now we have an additional term in this function. So we still have our Q function that reasons over the values of actions taken in states. We still have our exploration function U, but now we have another value function which reasons about transitions in the automaton, so that we can simultaneously reason both about states in the environment and the learned data representation of the neural network, as well as the automaton representation. So for each transition in the automaton, we're also going to learn values. We're going to learn an empirical expected value for each transition in the automaton that basically tells us how often that transition was part of a winning game. So the agent makes a move. Since we observed a new state in this tree that was empty before, we have to feed it through our neural network. The neural network gives us two things: the predicted optimal policy, which is a probability distribution over the actions, what probability you should go up, down, left, right, and the predicted value, which is the probability of winning the game based on the data that we have used to train the neural network. So these two things are used to update our Q value, our action value function, our exploration function, and our reward shaping function that is determined by the automaton. So here we're basically planning ahead both in the state space of the environment as well as in the objective space defined by the automaton. And we can continue doing this, building out this tree, similar to how DeepMind does. And here I have various colored trajectories in the state space and their corresponding trajectories in the automaton, just to show that for every trajectory of states, there is some trajectory in the automaton as well, because we're reasoning about both of these things simultaneously. And once we've built out this tree to be large enough, we take an action in the real world, we store the data, we train our neural network, just like DeepMind does. And we observe that over randomized Minecraft-like grid worlds where we randomize the placement of objects, averaged over 100 instances of 10 by 10 environments, our approach has a higher win rate than the DeepMind approach that does not leverage the automaton. Here, the win rate is the proportion of play steps, which are your real world steps that were part of a winning game. Right. So then we said, can we extend this to multi-agent settings? Not just multi-agent, but multiple teams with multiple agents, where each team can has its own automaton representation of the objective. This is a paper recently accepted in ICAPS 2022, and I'm happy to share it if anyone's interested. Here you have, this is one of the examples we looked at, is infiltrators versus guard. So the infiltrators are the two red agents. Their objective is simple. They have to obtain a key and then go open the treasure chest. The guard's objective, these are the blue agents. They have to find both infiltrators and monitor the treasure to ensure it has not been stolen. And here you see the automaton representations of both objectives. So here we have a sort of shared tree across both teams, across all agents, that simultaneously reasons about both kinds of automata. And what we observe is that we get some sort of basic cooperative as well as adversarial behavior by leveraging this approach. The cooperative behavior is a simple case of delegation. One infiltrator learns to pick up the key while the other infiltrator learns to go directly for the chest and open the chest. And then a more complex adversarial behavior where we observe an infiltrator kind of hover around the corner, staying out of the cone of vision of the guard, waiting until the guard is facing the right when the cone of vision is no longer a threat, killing the guard and opening the treasure chest, which is a fairly complex sequence of behaviors. But more importantly, going back to our objective, which is to improve data efficiency, when we use this multi-agent tree search with our automaton, we observe that on average, we can solve the game using only 53 actions, whereas the DeepMind solution takes 332 actions. So this is a significant improvement in the amount of data that we require. Right, so there's another aspect of efficient autonomy that exists outside of the actual discrete control algorithms themselves. They exist outside of reinforcement learning and planning, and this is the transfer learning setting, which is to say, how do you transfer learned decision-making information from one environment to another, which is of course very important when you consider the fact that in many real-world applications, we first train over a simulation environment, and then eventually that is to be adopted by a real-world system, perhaps some kind of robot or an autonomous driving system or some such thing. And so learning how to transfer effectively from one environment to another is very important. And we know that we've had tremendous success here in data analytics, in NLP and computer vision. So to briefly mention how this success comes about in computer vision, let's suppose that we want to classify this military vehicle. Clearly, there's not going to be much data for this particular kind of vehicle. Maybe we have 100 labels for this. And so if we try to train a deep model on 100 labels, it's going to be very, very brittle. It's not going to be a very good model. But what we can do is we can take a surrogate data set. Something like ImageNet, for example, is very common. We can train our learning model over the surrogate data set. And as we train this learning model, we're learning increasingly complex abstractions of the image space as it pertains to solving some classification problems. So at first we're learning edge detectors and we're learning curvature, we're learning basic primitives, we're putting them together and learning how to detect increasingly complex abstractions. So what does this mean? This means that a lot of those abstractions in the earlier layers will be useful to your target regardless. So you can freeze a lot of those earlier layers and you can simply fine-tune your learning model on the original test that you had. And even within the Air Force, we've actually had a tremendous success adopting this kind of very simple transfer learning. And of course, in NLP, a lot of the pre-training that we see with complex learning models is a form of transfer learning. So that lends some credence to the possibility that we might have similar success when it comes to autonomy. So one of the things I've looked at is how can we transfer these learned automata representations. So remember that in the approach I proposed, each transition in the automaton has an empirical expected value associated with it. So here, instead of transferring neural network parameters, what we're going to do is we're going to learn the automaton parameters in a source, simpler data set and transfer those to the target environment that shares the same objective. And so when we transfer it to the target environment, its reward signal at first is based on these learned automaton transition values, and then over time it anneals so that it can adapt to its own environment, because of course the environments are not going to be identical. The only assumption here is that the objective is identical, but the state space might be different, for example. Here again, we see some good gains in performance. So here we have three curves. The orange curve is if we apply the DeepMind approach directly on 25 by 25 randomized Minecraft grid worlds. The blue curve is if we apply the automaton guided tree search approach I mentioned earlier directly on the 25 by 25 environments. And the green line is what happens when we adopt this automaton guided transfer learning approach by first learning over random 10 by 10 environments and then transferring that information to the 25 by 25 environments. And we see that that gives us some significant gains in performance. The graph on the left here is averaged over 25 instances. And the graph on the right is just one very long instance where we're continuously randomizing the placement of the relevant features like the wood, the house, the tools, etc. Right, so finally the question arises, what if we don't have this automaton representation? Everything I've presented thus far, we assume that there's some end user that gives you this automaton objective. But in principle, one could learn this objective from the decision process itself. For example, in the game of chess, you might imagine that you have a reward signal, as I mentioned earlier, +1 if you checkmate your opponent, -1 if you get checkmated yourself. But there might be, for example, some automaton representation that captures a useful strategy that can be learned from that reward signal. Maybe the observance that a knight is in a particular position, that an opponent's rook is in a particular position, and so on. You might imagine that there's some kind of automaton there. So we've looked at, and this is joint work with Ashutosh and Taylor, we've looked at how we can learn these automata representations, both in the reinforcement learning context, as well as in the planning context. And we do this by adopting sort of a quintessential algorithm from active grammatical inference known as L-star, where L-star goes back to the 80s. And it's a very simple way of learning a language. It basically consists of having a teacher that can answer two types of questions. You can ask it, is this sequence of behavior in the correct language that I'm trying to learn? The teacher says yes or no. Eventually, you ask enough of those questions and you can build an automaton. And then you can ask the second kind of question. Is this the correct automaton? Yes or no? If the teacher says yes, you're done. If the teacher says no, it must provide a counterexample that is in the difference of the two languages, of your automaton and the true automaton. When you look at a lot of these older L-STAR papers, the practical limitations are brought up. Just who is the teacher, right? It's not always practical to assume that there's some all-knowing oracle that can answer these questions. But the interesting thing is that in the context of reinforcement learning and planning, your reward signal is the teacher. So when you ask the query, is this behavior in the language I'm trying to learn? The problem is now to find a decision-making policy that induces that behavior. Observe the reward. Is it positive? Then you're in the language. Is it 0 or negative? Then you're not in the language. And then for equivalence queries, it's a little bit of a hack. For equivalence queries, you perform your standard reinforcement learning or planning procedure for some predefined threshold of time. If no counterexample is found, we assume that we have learned the correct automaton. And so we've had some success there. In reinforcement learning, we've managed to learn some of these structures. In planning, we've managed to both learn these structures and then leverage them to improve the learning process. I'm way over time. Okay, well, this is the conclusion slide anyway, so I thought you were gonna keep me, hold me accountable on time, Ashutosh. All right. Anyway, I'm concluding. So reinforcement learning and planning, as I presented, we've had tremendous successes: AlphaGo, AlphaStar, OpenAI 5, DQNs, Liberatus, and so on and so on. But these state-of-the-art systems are simply far too data hungry to be adopted by the general public and by academics and by anyone that doesn't have tens of millions of dollars in power budgets. So I've been looking into how we might address that through the lens of not just neurosymbolic AI, but more specifically neurolinguistic autonomy, where we ground the symbolic component in formal language theory and use that to accelerate the learning process. And finally, as a takeaway, I just want to say that as a community, we've spent a lot of time and resources, justifiably so, on developing better and better learning models. But I think we should similarly spend more time on developing better and better representations of our objective, and that ultimately the marriage of these two things into neurosymbolic autonomy, I think will give us the next big leap in efficiency and finally enable the adoption of these systems. So with that, I thank you for your time. And do we have time for questions? Yeah, we do. I open the floor to questions. There's some hands raised. How do I handle this?
Evan, do you want to unmute and start with questions?
Yeah, sure. I was more first clapping, but of course, thank you for the nice talk. Yeah, so I mean, I'm intrigued in sort of your discussion about like using these particular symbolic representations for, somehow like getting rid of the sort of, I don't know, the huge cost of training and such. I mean, can you talk a little bit about what you think might be like the limitations of this, kind of like how much sort of like hand tuning of these like representations where we're going to need to do in order to be able to get this kind of savings, or just kind of talk more generically about that?
Right. Well, the main limitation right now is that I haven't seen any work that goes past the regular languages. So we're limited from an expressive standpoint in the kind of objectives that we can represent. You might imagine that, for example, ideally, we could just reason about Turing machines altogether and have the ultimate level of expressive power. So we're limited from that expressive standpoint. But even this integration of symbolic structures is ultimately not going to solve the efficiency problem alone. And I do suspect that what we're going to need is some next leap in learning that moves us past backpropagation. Backpropagation, of course, has been tremendously successful. But when you consider the fact, as I alluded to earlier, that these quote unquote superhuman systems are cheating in some sense because humans don't have nearly as much time to learn as they do. And even in the case of planning, a human expert in chess maybe evaluates 100 positions in advance, right? If you're that good. But if you look at a state-of-the-art, planning solution, something like Stockfish, it evaluates millions and millions of board positions. If we were to limit the state-of-the-art to only play as many games as a human player can play in its lifetime, and limit it to only evaluate as many positions as a human player can evaluate in a single move, they would fail miserably. And I think this is more of a limitation on backprop-based learning. Now, what would replace backprop, I have no idea, but that's just sort of my intuition.
Thank you.
Majid also has a hand up in the Zoom.
Hi, Alvaro.
Hi, Majid.
Thanks for the nice talk. So I have a question about this slide. You were talking about multi-agent planning. So there were two options, right? Cooperative and adversarial.
Yes.
So I'm just wondering the way you solve, there are two questions here, right? I'm trying to see the complexity of cooperative versus adversarial. I want to see which one is more complex to solve. And then the way you solve it, is it in a compositional way, or you take the product of all the agents and then you solve the overall problem on top of the product? Thank you.
Yes, so this is not based on any kind of product decision process. The way this works is we build this decision tree where at each level of the tree, it's a different agent taking its turn. So it's turn-based. Infiltrator 1, then guard 1, then infiltrator 2, then guard 2, then infiltrator 1 again. And so each team is learning a good policy for its adversary under the assumption that the adversary was going to play intelligently. So that's an assumption that's sort of being made there, because of course you can have irrational adversaries and that makes things tricky from a game theoretic standpoint. But that is how we're doing it. We're taking turns within the tree. And as far as the complexity, I would say the adversarial is more complex. When you look at this particular test case, the adversarial is a total of at least 8, 10, something like 14 or more actions that entail avoiding the guard in this particular instance and then moving in for the kill and getting the chest. The cooperative is fewer actions and it's simpler actions. It's going to the key and then going directly to the chest, which is from a learning perspective, what might be going on is that the agent is learning to minimize for example, the Euclidean distance from it and the treasure chest, which, I mean, wouldn't be all that impressive. But in the adversarial setting, that doesn't seem to be what is going on, because the agent is getting further away from its objective, then getting closer to its objective, depending on the behavior of the guard. So I would say the adversarial in this case is much more complex and more interesting.
So can I ask another question?
Of course.
Yeah. So the objective, is it in the form of an automata, and is it like for each agent is given, or you have a global automata for the whole multi-agent setting?
You have a global automaton for each team. So here you have 2 teams, 4 agents, and 2 automaton. And so each agent from their respective teams traverse their automaton when it's their turn.
And this can be extended to more than 2, right?
Yes. Yeah, this can be n number of teams, and each team can have m agents. Of course, as you increase these numbers, it can become quite slow to learn. But it's, in principle, it's possible.
Yeah, thank you.
I don't see any hands up. I don't know if in the audience anyone.
Just one quick question.
Yeah.
Yeah, so trying to
mean, thanks for explaining a little bit about the limitations of the work. Just in that vein, since I'm not really a formal languages person, the game of Go, can that be played with a finite state automaton?
You know, I'll be honest with you, I don't even know how Go works.
Oh, really? You place a tile on one of the intersections of,
Yeah.
and you have 2 players. So, and you're trying to essentially surround the other players' tiles that they've played.
I think there should be strategies that are encoded as automata because I know part of the objective is to capture territory in Go. So you might imagine that there are patterns of black pieces that could correspond to.
So it wasn't just, this isn't a question on Go. It's more of a question about the extensibility of this framework. So I was trying to understand, like, what are the game-based limitations that could come up based on the number of possible plays that could be executed, and whether or not there's an increasing amount of overhead, for instance, in dimensionality of the game, or a number of states and actions that could be played. That in the case of AlphaGo was sort of just rolled over like a tank because of they were able to do these many rollouts. But in your case, you might not see the same sort of improvement as a result of trying to encode these rules at the outset. I was trying to get some insight.
Yeah, there is an assumption that is made here that there is a low dimensional set of meaningful events that define the alphabet of the language that you're trying to learn. So for example, in the case of Go, it becomes a lot trickier. If there's a one-to-one correspondence in language space and action space, there's no point in even adopting this. But in the case of something like Minecraft, where the objective is defined over a few observable events like the wood and the factory, etc., then you can have an arbitrarily large state space. Your automaton will still be small because it's defined over this.
So maybe you could see
small alphabet.
If moving out of the finite state automata regime in the hierarchy of languages were possible with something like this, then maybe it could be extended to other types of scaling of those.
I think that would be interesting to look into.
Cool.
It's a good point.
Another question would be, how do you get those predicates like in the system? Is it often given? Because to start a language, you need to somehow finitize the alphabet or something. But in some of those settings, like they look like it's not even clear what are the interesting features in the environment.
Right. And that's something I could talk about for hours. It's something that really interests me. Usually you assume that it's given. In some settings, this is reasonable because you have very sophisticated object detectors out there in the wild. Tools like YOLO, you only look once or you only learn once. I forget what it stands for, but there's very sophisticated object detectors that can look at a scene and tell you these are the objects that are there, and that could define the atomic propositions or the letters of your alphabet. And then that will in turn define the language using approaches like this one. What would be more exciting is if you could learn those semantics through experience, so that they're not given to you. As you know, this is something I've looked at unsuccessfully by taking disentangled autoencoders, taking the learned parameters of a neural network, feeding it through the disentangled autoencoder, and then by the disentanglement property where each neuron in the autoencoder is independent of all other neurons, defining those as the basic atomic propositions and trying to learn over that, which in my head makes perfect sense. But in practice just doesn't work. So that's something I'm still investigating. I think that would sort of be one of the holy grails of neurosymbolic AI more generally, is if you can learn the semantics as opposed to have them given. When I showed the 3 examples in neurosymbolic AI, for example, those semantics were given. They were overlaid straightforwardly on your learning system. And even those simple overlays gave you good boosts to efficiency. So imagine if you could actually learn the semantics wholesale. I think that would be very powerful.
Are there any other questions?
Yep.
I would follow up on Chris's point. I was curious, like, when you think about real world problems you're trying to solve, like how this framework would kind of transfer to that in terms of just bigger, kind of larger scale problems, and also just kind of like messier real world kind of content.
When transferring from simulation to the real world? So of course, no matter how good you try to make your simulation environments, there's always the problem of data shift, which is why I think transfer learning is so important. But it's also why I think neurosymbolic transfer learning is important, because if you only transfer the parameters of a neural network from one environment to another, you're transferring the learned data representation. And because of that data domain shift, like you said, the real world is messy. You're not going to observe the same state space as in your simulation environment. What I was trying to get at in my neurosymbolic transfer learning approach is that we can transfer such that the two environments are different, the state spaces are different, the features are different. As long as the semantically meaningful events that define your language are the same, you can transfer over the symbolic representation. And so I think that's going to be one powerful way to transfer between two environments that don't have the same state space, but that have the same objective. That is the assumption being.
Do you have any specific ambitions for real world kind of problems?
If I can get my hands on a like autonomous car, you know, I would love to go from the Carlo simulator to the autonomous car. That would be awesome, you know. Ashutosh claims to have this elusive vehicle. I haven't seen it. I was here for 2 months. He never showed it to me. But if he has it, I'm happy to take a look.
Okay, so I mean, there would be some more time to have questions over here, but let's formally end this presentation now. Let's thank Alvaro again.
Thank you.
Do you still want to ask your question before I end the Zoom?
I mean, I can ask him over dinner.